Hello everybody, this video is going to be about Gibbs free energy. It's the last video in our thermodynamics chapter. Here's a target for you. The thing you should come away with at the end of this lesson is that we're going to be able to use the relationships between a variety of things to solve for all sorts of stuff. This is basically a game of algebra. So we can use the relationship between Gibbs free energy, enthalpy, entropy, and even equilibrium to try to solve for whatever it is we're interested in. There's going to be lots of algebra here. It's going to be a lot of rearranging, a lot of substituting. You're going to have to remember which equations you can set equal to each other. And while it may seem overwhelming at first to have so many different equations and to be doing so many manipulations of them, the thing that you will learn really quickly is that it's very powerful to be able to set these things equal to each other, and you can solve for a lot of things when you feel like you're missing information you wish you had. So that's kind of what we're going to focus on today. So the Gibbs free energy is the energy that's available to do the work in our system that we're interested in. You may sometimes hear people call it a chemical energy, chemical potential. We will be using the term Gibbs free energy. We use the symbol of G. We can relate the entropy of the universe to this energy that's available to us through the equation you see here. Remember, we'll be using kelvins for our temperature. So we have information here about our system. We have the enthalpy of our system, we have the entropy of our system, the temperature, and we're able to relate that to the universe. That's going to allow us to turn it into this very, very important equation. This is called the Gibbs-Helmholtz equation. We're going to use this a ton. This is one that we for sure should have memorized. We should always be thinking about this one. This is what connects our enthalpy and our entropy and our temperature to the actual amount of energy that's available to us. Very, very important equation. Now, because the entropy of the universe, that change in that entropy is what decides whether something's spontaneous, and because we can set these equal to each other, delta G can be used to determine what's spontaneous or not. Remember that we want the entropy of the universe always increasing. That's what's required for something to be spontaneous. And if you notice this little negative sign here, what that results in is that delta G must be a negative for something to be spontaneous. If that reaction is going to occur in the forward direction all by itself, it needs a negative delta G, because that is implying that the entropy of the universe would be increasing, which we already have learned is what makes something spontaneous. So that right there is very, very important fact. That should be memorized. You should be able to shout that out to me without even thinking about it. Knowing that it needs to be negative is what's going to allow us to do a lot of thinking about our numbers and prediction about our spontaneity. If you can decide whether it's negative or positive, you can decide whether something's spontaneous or not. A lot of this is mental math. A lot of this is not necessarily crunching the actual numbers. Sometimes all we need to do is rationalize and think through the logic and decide, based on the numbers I'm given, would my answer be positive or negative using this equation? You can save a lot of time not having to actually punch the numbers in your calculator. You may not even have the numbers. You may just be told it's exothermic and that you're going from a solid to a gas. Well, that allows you to decide the plus or minus algebraic sign on your enthalpy and your entropy. And if you can think about those, you can kind of predict what the sign on delta G would be. Some people love this kind of mental math, and sometimes people get overwhelmed. If you are one of those people that gets overwhelmed, you have to think through it in baby steps, one piece at a time. There are lots of handy charts that you can find that try to break it down for the people, who tend to get overwhelmed with mental math, where you're talking yourself through, okay, if this one is positive and that one is negative, then this one has to be what? So let's go through one of those versions of the chart. You should have a glue-in with 2 different versions. I don't care which one you like. Use whichever one is good for you. If you find a really cool one online, then send it to me. I'm happy to add it to our reference sheets. Okay? So let's walk through some of this mental math. We are going to look at what the best combo would be that would result in having a spontaneous reaction. Exothermic would be preferable. This value here being negative sets us up for a good position for our delta G to end up negative. Increasing that entropy, having more of those microstate arrangements, that's preferable, that's favorable. If this is a negative value and you are subtracting a positive, you're going to get a bigger negative, aren't you? That's what we want for it to end up spontaneous. If you have something exothermic and you are increasing the entropy, that will always result in a spontaneous reaction. That's the best combo you can have. And it doesn't matter what temperature you're at, does it? It doesn't matter if you're at a low temperature or a high temperature. You will always be taking a negative minus a positive to get a negative answer, regardless of what your temperature is. So that's a great scenario there. Negative minus any temperature positive value for your delta S will always give you a negative. So you can see I don't have to have any actual numbers here, do I? My algebraic signs will only result in one answer, which is spontaneous. Now let's go to the opposite extreme. Let's look at the worst combination, the one that's not going to be spontaneous ever. If we have an endothermic reaction and our entropy is decreasing, that's never going to be thermodynamically favorable. That's never spontaneous. Doesn't matter what temperature you're at. If you have a positive number and you are subtracting a negative, no matter what temperature you're at, you are always going to end up with a positive delta G. You will always end up with a positive, non-spontaneous reaction. That double negative right there is the key. Really important to understand that if you have endothermic and you're getting less entropy, really bad. The other combinations are what we call variable. Not quite as straightforward. So for example, if you have an endothermic reaction, but your entropy is increasing, there is a way for that to end up spontaneous, but only if you're at a high enough temperature. So let's kind of break that down. If we're endothermic, we're going to have a positive for our enthalpy, and we are subtracting a positive number. So if I want to get a negative number, my delta T needs to be sufficiently high that this second piece is bigger than the first number we have. So delta H has to be a smaller number than our T delta S component. A small number minus a big number gives you a negative number. This is a time where you may have to do the actual math. You may have to actually calculate it out because you're going to have to decide mathematically, is this at a high enough temperature that the entropy wins? We are trying to get that entropy increase large enough to overcome that unfortunate endothermic part. We need the entropy to dominate, right? We need that to be bigger contribution than that endothermic piece. Now there's another combo that's kind of variable. What if this time we have an exothermic reaction? That's thermodynamically favorable. That's good. But our entropy is decreasing. There is a way for that to end up spontaneous, but this time it needs to be at a low enough temperature. So let's walk through the positives and negatives and think about this one. If I'm exothermic, I have a negative number. But I'm subtracting a negative. If I want that to result in a negative answer for delta G, what I have to do is make sure that this second piece is small enough that I don't end up with a positive here. That double negative that you're going to have is problematic because you're basically taking a negative number and you're adding a positive number, and if this is too big, you're not going to be able to stay at a negative value. So this time we need that temperature component to be low enough that the exothermic nature, that enthalpy, can overcome the decrease in entropy. So the enthalpy piece needs to win. It needs to be more negative, right? It needs to be a big enough negative compared to the low temperature decrease in entropy component. And if you can make that happen at a low enough temperature, then it can be spontaneous. So like I mentioned earlier on, sometimes people end up with their brain feeling a little scrambled here. You're talking about negatives and positives and double negatives, and if this one's small and that one's big, it can be a little overwhelming. If this is really tough for you, then just memorize it. Memorize the combinations that would be most thermodynamically favorable, the worst, unfavorable, and then those variable combos. You can literally write out your equation with pluses and minuses. I hate memorizing stuff. I really do. I am just too lazy for that. I would rather mentally process and walk myself through it. The problem is that takes time. And so, when you're taking that time to test, do you have the luxury personally to be able to walk yourself through it? Or do you need to memorize it if this is tough? That's a personal decision. I can't make that choice for you. But you need to do something, okay? I mean, maybe you find some mnemonic online, right? If you find something cool, let me know. But whatever you do, you can't shut down. You can't just say, oh, I'm overwhelmed. I don't know. You have to push through that. And you got to do some mental math, and you got to figure it out. This is a topic that comes up often on the FRQs. This is one of the gluons you have, so you can see I kind of showed you all the different combos that you might end up with. The one I printed for you is in black and white. You can always print a color copy online if you want, or color code it. This is another one. I found this, recently. This one I think is nice because it kind of simplifies it down a little bit more. This reminds me of biology when you're doing those little Punnett squares. So, how would you calculate it? If you want to do more than just mental math, if you're not just trying to decide spontaneous or not, then there's a couple different ways that you can calculate the actual delta G. The first is using that Gibbs-Helmholtz equation. If you have enthalpy values, you have temperature, you have entropy values, right, and you're not doing anything weird like changing your temperature, you have standard states from a chart, you can just plug those values in and calculate your delta G. Pretty straightforward. A second way you could do this is by using Hess's law. If you're given equations and you're given delta G values, you can do the same thing you would have done with enthalpy. You can combine the equations, flip them, multiply them, right? Cancel out things on both sides, add your values together, figure out what your delta G is. So you can see here that going from diamond to graphite is a spontaneous reaction that happens very slowly over time. Clearly not during our lifetime. It's not like our diamond jewelry is suddenly turning into graphite in front of our eyes. But you can see, technically, it is a little bit negative. A third way to do this is similar to just a products minus reactants like you've done for a variety of things. Using those formation values, just like you did the heat of formation subtractions, you can do the same thing here with your delta G values. So it just depends on which data you're given. Depends on your preference. If you have access to all sorts of data, you could choose which of these you prefer to do. Quick comment about pressure. So enthalpy is not pressure dependent, but entropy is. The entropy depends on the volume because that impacts the places you can arrange those atoms. It changes the number of microstate arrangements. And so your Gibbs energy could change based on pressure because that entropy component is changing. So the larger your volume, the more entropy you have. Lower of that pressure, more entropy you have. The nice thing is the problems we do tend to be simplified. We're not going to be changing all sorts of variables at one time or things get way too complicated. But it is something that you should know in case you're trying to choose a more favorable condition. It's good to know how the entropy is impacted by that pressure and therefore how Gibbs is impacted. Let's start looking at the connection between Gibbs and equilibrium. Now, equilibrium in general is a complicated concept, and then you add to that the thermodynamic aspect, and it can seem a little more complicated at first, but I think understanding how thermodynamics impacts and is connected to the equilibrium actually helps explain what equilibrium is and why it's occurring. So the most important thing to understand here is that at that equilibrium position, your change in the Gibbs is 0. You'll notice this does not have a not symbol, okay? We're not doing this at those perfect standard conditions. We are literally dumping stuff into a beaker, okay? And so equilibrium is defined as the point at which you have no change in your Gibbs energy, where no direction is better than the other. You saw this graph on an earlier lesson. I'm trying to show it to you multiple times as we go through this topic. Now, if you dump your chemicals into a beaker and you have too many reactants, when your Q is smaller than that K value, what ends up happening is the forward direction is spontaneous until you get to equilibrium. you can see going that direction, you have a negative delta G. You're losing that energy, right? Now, your reaction is not going to keep making products once you get to equilibrium. Because if you kept going forward, your delta G becomes positive, which is not thermodynamically favorable. That's not going to happen. It's not spontaneous. And so you get to this point, and going forward or backwards, right here, there's no change in your delta G. That's what equilibrium is. Back and forth is okay because there's no change in your delta G. Now, if you dumped your chemicals in your beaker and you had way too many products to begin with, then the backwards reaction is spontaneous because that's going to result in the negative delta G until you get to equilibrium. And back and forth here, no change in that free energy. That's why it's allowed to happen. That's why this point is special. We are trying to get to equilibrium because at that point, right, that's where you have your delta G equaling 0. You can figure out where you are on that graph by using this equation. Delta G is what we have when we have some non-standard condition, right? We've dumped a bunch of stuff in our beaker. Delta G naught is what we would have at standard conditions. If we get that from our chart, right? That's other people have done a bunch of work for us. We have access to this information. And then you can see here, what is Q? Q is similar to our equilibrium value, right? But it's what we actually have when we've dumped our chemicals into the beaker. Not what it would be when we're finally at equilibrium, but it's what we're currently at when we've dumped those things together. Okay? So this allows us to figure out kind of where are we and how far are we away from that equilibrium position. If you can calculate your delta G, you can figure out on which side of that graph you're on. And you can figure out which direction you're going to proceed. So if my delta G is 0, I'm at equilibrium. If my delta G is negative, then the forward direction is spontaneous. I'm going to go to the right. I'm going to make more products. If my delta G is positive, I already have too many products. The backwards reaction is now spontaneous, and I'm going to be moving to the left, making more reactants. You are used to thinking about this shifting by comparing your K value and your Q value. But we can also do this thinking about delta G. You might not have access to this information. Maybe you don't know what your K value is. But if you can calculate a delta G, you could also figure this out, so it allows us a different way of answering equilibrium questions. Now, thinking about this equation, if we know delta G at equilibrium is 0, because there's no change, right? And we know at equilibrium K and Q finally equal each other, then I could substitute those in. And then can't I rearrange this, move this to the other side? And I find out that delta G naught is equal to negative RT ln of K. And the R value that you would use would be this one. Remember, you have different R values. Constants, just, with different units on them. Use that one. We call this the Ratlink equation, just a silly way to remember it. Delta G naught equals Ratlink. So if you know what temperature you're at, and you know your equilibrium constant, you can figure out what the delta G naught value would be. So that's a very handy equation. Maybe you're not given your delta G information. You don't have access to a chart or an appendix or anything. You don't have enthalpies. You don't have entropies. You don't know how to get this. But you do know your K value, and you do know a temperature. Then you can figure out what it would be. One thing I want to remind people of that tends to come up when using that Ratlink equation is that if you are doing any kind of Hess law manipulation, you are going to have to edit your K values as well. And I see people forget that. So if you multiply an equation, you got to raise K to that exponent. So if you double your reaction, you're actually going to square your equilibrium constant. If you're taking half of the reaction, you have to raise it to a 1/2 power. If you add your reactions, you have to multiply your K values. Make sure that you do all of that before you plug in to that equation. You don't want to use the wrong K value here. So if you have to manipulate your reactions at all, make sure that you manipulate your K values. People tend to forget that. Okay. Let's look at another manipulation of this that we can do. Now we know we have this Ratlink equation, and we know the Gibbs-Helmholtz equation. And if those both equal delta G naught, can't I set them equal to each other? So I end up being able to say that negative RT ln of K equals delta H minus T delta S. Ratlink equals Gibbs-Helmholtz. That is an incredibly helpful rearrangement because it's going to step us towards being able to graph some data to calculate things that we might need. So if I take this rearrangement and I'm trying to solve for the natural logarithm of K, it ends up looking like this. I've divided both sides by RT. Over here, the T's end up canceling. So I get negative delta H over RT. I got a double negative here, so now this is a positive. And I have my entropy over the R value. If I reformat it like this a little bit, we can see that the equilibrium constant is inversely proportional to our temperature, isn't it? And now, doesn't this kind of look like a linear equation? Y over here equals mx plus b. Now I can graph it. I can now use the intercept to help me find my entropy. And I can use the slope to help me find my enthalpy. So I can graph this stuff and I can get those pieces of information that I need. So what you do is you end up graphing the natural logarithm of your equilibrium constant versus 1 over the temperatures. Because remember, your equilibrium constant changes based on the temperature that you're at. Each temperature has its own K value. So if I can get the K values for lots of different temperatures, I can graph those. And I'm going to get a linear graph. I use Excel or a graphing calculator. Doesn't matter which one. And you can find the line of best fit. It gives you an equation, and that equation mimics this one up here. Your slope is negative delta H over R, and your intercept is delta S over R. Multiply those numbers that Excel gave you by your R value, right? You can figure out what those thermodynamic pieces of data are that you might need. Delta H and delta S. Very, very handy. Now, there's so many rearrangements. There's so many ways you could set things equal to each other. You gotta have decent algebra skills. If your algebra is not your strong suit, then you need to practice and practice and practice. You have to develop some muscle memory for ways you can rearrange these equations. One thing you might want to do is every time you come across a rearrangement, you can make a little cheat sheet and you could write it down. I also encourage people to not try to do your algebra in your head. Try to just do it on your paper, right? That can be very helpful if you're struggling with your algebra. So let's do a couple practice problems. For this one, you're given some entropy data. Why don't you try to calculate the entropy of that oxygen? You can pause the video if you need some time to do it. So you have enough information here that you can just do a simple products minus reactants. You know what the overall reaction is, so you plug that in here. You have 2 moles of your product minus 2 moles of one of your reactants, and you're looking for your other one. Remember that that not value for entropy for an element will not be 0. The entropy, there's always a value for that one. That one always has a value. Sometimes you may have to do something like this before you can do the next part of your equation. You may have to solve for S and then solve for delta H, and then you can solve for delta G. So they're all connected together. You may have to do multiple steps. They may not just tell you what delta S is. They may not tell you what delta H is. So on this next one, the nice thing is they did tell you those values. You don't have to find them out yourself. They told you delta H, they told you delta S. You can just get straight to finding delta G. So pause the video if you need some more time to work this one out. So you're going to be able to use that Gibbs Helmholtz equation. You're able to just plug in all your numbers. Remember, we should be at Kelvin for our temperatures. And then the other thing is you need to be very careful that your units match. We have kilojoules over here, but we have joules for our entropy. They love to get people on that. Now, it doesn't technically matter which one you convert. If you go to joules for both or kilojoules for both, it doesn't really matter. It is more traditional to have delta G come out in kilojoules. So just be a little bit careful with your units. That's something you're going to notice all year long. Really, really trying to get you to be careful about those units. Sometimes you may get a question that at first glance doesn't really seem to be about Gibbs free energy. It doesn't mention it anywhere in the question. So something like this, where it's asking you to calculate the boiling point of a substance, and then they give you enthalpy and entropy values, and people kind of go, wait, what? So you have to remember that phase changes are equilibriums. Going from liquid to gas and gas to liquid for this substance is an equilibrium. And so if we know that delta G is 0 at equilibrium, that is my connection between thermodynamic data and an equilibrium question like, at what temperature does this occur? So because that's equal to 0, I can use my Gibbs-Helmholtz equation. I can do my subtractions to get delta values for these things. And I set them equal to 0 because I understand that at equilibrium, phase change, delta G is 0. Now I only have one variable to solve for, which is temperature. I was careful that I put my delta H and my delta S into the same unit, and out comes my temperature. Trying to connect these two chapters together is a very common thing we're going to see. Now, sometimes they're going to ask you a question that doesn't seem to even need math being done. Like, here's a conceptual question. Under standard conditions and at 298 Kelvin, what substance or substances will be formed? And then they give you a Gibbs value. And people go, wait a second, I don't feel like I have a lot of numbers. How am I supposed to put stuff in an equation? And you're not supposed to. All you're supposed to do is think about the algebraic sign on your delta G. So if you notice, that is a positive value. That means for the way the reaction is written, going in the forward direction is not thermodynamically favorable. We are not going to make our products. The backwards direction would be favorable. So I'm not going to make nitrogen gas and hydrogen gas. The reverse reaction is actually going to occur. And we're going to end up making NH3. So don't feel like every question needs a calculation. Sometimes they do, sometimes they don't. Now this question, same exact question, but this time maybe it asks you, well, what's the equilibrium constant? What is your value of K? You know your delta G, you know your temperature, and you're solving for K. You want to know your equilibrium constant. You probably can recognize quickly that you're going to use the Ratlink equation. Then sometimes people's algebra skills falter. They forget how are they going to solve for something that's inside a natural logarithm. They can plug in all their numbers and then they forget what to do. So what you want to do is you want to simplify this down, divide both sides by all these numbers so that you get just that ln of K value. Now we have to remember how logarithms work. Okay, remember a natural logarithm is a type of logarithm, similar patterns. If I want the natural logarithm of a number, right, we're trying to find this number, natural log of y equals x. So if I want to solve for y, I have to undo that natural logarithm, which is going to be taking e and raising it to the thing that was your original answer, to the x. E to the x gives you whatever's inside your natural logarithm. So K is what I'm after. So I'm going to do E raised to this number here. And that's how I get my K value. So if I know my Gibbs value, I can figure out what that equilibrium constant is. I don't have to know concentrations and set up a law of mass action and do an ice table and like all that stuff everybody always wants to do with equilibrium. We don't have to do all that. Not all equilibrium questions are ice tables. Some equilibrium problems are thermodynamic questions because those topics are interconnected. So I know that was a lot of math. I know that was a lot of algebra. That was weird trying to smush two topics together that you're not used to combining. But I think after a little bit of practice, you will start to see how easy it is to go back and forth between equilibrium and thermodynamics topics. All right, everybody, that was it. I hope that was helpful. Bye.